Hi there, and welcome to our lecture on motion and force. This is Motion 3 of Unit 5. Our key ideas: what do scientists identify as the fundamental forces of nature? What happens when there's a net force acting on an object? What force always opposes motion? And why is friction sometimes necessary? So start looking at our first question about fundamental forces. These fundamental forces are the forces of gravity, electromagnetic force, strong nuclear force, and weak nuclear force. Strong and weak nuclear forces act over a short distance, whereas the force of gravity is a force that you feel every day and can act over a longer distance. Other everyday forces, such as friction, are a result of electromagnetic force. So these fundamental forces vary in strength. Fundamental forces vary widely in strength, and the distance over which they act, and actually as the distance increases, the force will decrease, or if the distance increases or decreases, if the objects get closer together, then the forces will be greater. And these forces can act through contact or over a distance. And contact forces, examples of these are pushes and pulls. So pulling on an object or pushing on an object is a contact force, the actual physical touching. Field forces, such as gravity, don't require that the objects touch each other. If we throw an apple or a ball up in the air, it's going to come back to the earth. So there's not actually anything that we can visibly see touching the apple, it just comes back down. It's field force. And both contact and field forces can cause an object to move or stop moving. Next question: what happens when there is a net force acting on an object? So whenever there is a net force acting on an object, the object will accelerate in the direction of the net force. And to define net force, this is the combination of all forces acting on an object. So if we have an object, and we're pushing this way with a force, and we're pushing this way with a force, and then we've got the force of gravity, and then we've got the normal force of, say, the table or the surface it's sitting on. So all these total forces, if we were to apply numerical values to these, they equal the net force. But if the net force is greater in one of these directions, let's just draw like this arrow longer, and saying that it's pushing in the direction of the arrow, the net force on this object will be to the right then, because this longer arrow indicates that we have more force pushing on this object, so it pushes it to the right then, or pushes in the direction of that greater force. Balanced forces do not change motion. Forces are balanced when the net force is 0. So if we have a light hanging from the ceiling, the upward force of the cord, the wire that's holding the light to the ceiling, is balancing out the force of gravity. So it's keeping the light from crashing to the floor. That would be balanced. Whereas an unbalanced force do not cancel completely. So if that light all of a sudden falls to the floor and crashes to the floor, then we have an unbalanced force, so the force of gravity would be greater than the tension holding that light up to the ceiling. And if I think about that previous example where I pushed on a little square object, whatever it was, make that square, the unbalanced, say this force is greater than the other forces acting on this object. Therefore, the net force is not equal to 0. So we have an unbalanced force. And again, it's going to accelerate in the direction of the net force. So where the arrow was pointing, that's where it'll accelerate to. So in the example, if you push a box to the east and your friend pushes the box to the north, well, if they're equal forces, then the box is going to go northeast. Alright, the force of friction. Force of friction is the one that always opposes motion. And a further definition, besides opposing motion, it's going to be between two surfaces that are in contact. So for friction to take place, the surfaces do have to be in contact. And there's different types of friction that we're going to discuss. So static friction is greater than kinetic friction. And static friction is the force that resists the initiation of sliding motion between two surfaces that are in contact and at rest. So basically, static friction is a friction of object that is not moving. So static is non-moving friction. So a book sitting on a table not moving is an example of static friction. Whereas kinetic friction is the force that opposes the movement of two surfaces that are in contact and are moving over each other. So if I were then to push that book across the table, then I would have an example of kinetic friction. We can subdivide or further break down kinetic friction into different categories. We've got sliding friction and rolling friction. Again, these are just examples of kinetic or moving friction. Sliding when an object slides past. Rolling when a rounded object rolls over a surface. So that would be rolling friction. And typically, if we have an object that's the same weight, we can obviously tell that rolling friction is a lot less. So it's easier to roll something than to push it or slide it across the floor in most cases. So that's why sliding friction is greater than rolling friction. Okay, so look at our last question. Why is friction sometimes necessary? It's necessary for many everyday tasks to work correctly. We've got unwanted friction that could be lowered using low friction materials such as non-stick coatings on cook pans, or we can use lubricants such as motor oil, wax, and grease so the engine parts move past each other a lot easier. We can increase helpful friction when we scatter sand on icy roads or salt. We're increasing the friction on those surfaces to keep us and cars from sliding around. We can wear textured batting gloves when playing baseball to make it easier to grip the bat so it doesn't fly out of our hands when we hit the ball. Without friction, we wouldn't be able to drive or really do much of anything. We couldn't walk from class to class. So without friction between the tires and the road, tires would not be able to push against the road, and the car would not move forward. Just sit there and spin. The force pushing the car forward must be greater than the force of the friction that opposes the car for the car to move forward. And that's a fairly logical statement. You've got to accelerate or move, give more power to the engine to move to overcome that friction that's keeping the car at rest. So because friction, a constant force, must be applied to the car to keep it moving at the same speed. If we were to remove our foot from the accelerator, the effects of friction, air resistance, and gravity all come into effect on the object or the car and slow us down. Alright, so a few examples to finish this up. When a car moves at a constant speed, the force moving the car forward exactly balances out the friction. So this is a balanced force. There's a constant speed. If we accelerate, though, the force of the object, the force of this car, is greater than the opposing force, the frictional force. And then if we're parked on a hill and we're not moving, again we've got balanced forces because the object's not moving. So the parking brake or the tires, the surface is opposing the force of gravity to make that car roll down the hill. So, thanks for listening.